In case the label value is 1, if the label value is 1, what you do is the second component gets nullified because 1 minus 1 is 0. Anything multiplied by 0 is 0. So the second part of the equation is 0. So what you have is only the first part. If the output value is, if the actual value is 1, so you will, what you do is you will consider only the first part of the equation. So I'm reiterating again, this binary cross entropy or log loss function, even though it looks like a huge mathematical formula, it is very, very simple. It has two components, two parts, first part and the second part. So whenever the label value is 1, the second part is nullified. Only the first part is taken. So what you do is you take the actual label value and you multiply the log of the predicted value. So you take 1 multiplied by the log of the predicted value. Here in this case, the log of 0.7.
Excuse me, sir.
Yeah,
Sir, PPT is not visible, sir.
my screen is not visible. Thank you for telling. You
Yes,
should have
sir.
told me long back. Okay, just I'm sharing my screen then.
Okay, sir.
Is it visible now?
Yes, sir. It's visible, sir. Please continue, sir.
Yeah, team, I'm really sorry for my assumptions, assuming I assume my screen was visible. So don't bother, please feel free to speak or chat, whatever it is, whenever you are unable to see my screen or whenever you are unable to understand. Don't be quiet. Be bold enough to talk, right? So are you able to
Okay, sir.
see my screen?
Yes, sir. Yes, sir.
So
Please
are you able
continue.
to see the formula log loss of binary cross entropy? Are you able to see it?
Yes, sir. Yes, sir.
Okay. Okay. So what I'm talking is this regression losses, absolute mean error and the mean square error and the root mean square error. They are good only for regression models. In other words, they are good for predictions, but they are unfit for classification problems. So in order to have a loss function that is good for classification problems, we have another loss function called binary cross entropy. It's called binary cross entropy. This is also called as a log loss. So what you do here is the label value of any binary classification is either it has two outcomes, either 1 or 0 or any two outcomes. If one is true, the other becomes false. If other is false, the other one becomes true. So it is either 1 or 0. So this log loss or binary cross function, the equation you can see in the screen. If you ignore this sigma and 1 by n, you can see this equation is divided into two components. Y subset I into log of y hat plus 1 minus y subscript I into log 1 minus y. So whenever the label value is 1, whenever the label value is 1, the second part of that equation becomes 0 because 1 minus 1 is 0 and this part will become 0. So the items or the equation that we are left is simply y subscript I multiplied by log of the predicted value. So here in this case, the prediction will be yi 0.1. Once you get this error, you sum it up, then you do the average, then negate the sign. This process is called the binary cross entropy. So mathematically, it is represented as minus 1 by n, which is nothing but the average times the summation of y subscript I times log y hat plus 1 minus y 1 minus y dash y 1 minus y subscript I times log of 1 minus y hat. So since it is a binary classification problem, only one part of the equation remains and the other thing is cancelled. So once you're done with it, what you do is you sum it up and take the average and you multiply the sum average, you multiply the average by a negative sign. That is how you get the binary cross entropy. So this is used in logistic laws and all the classification related problem. So what we have discussed now, as far as this log functions are, we talked about regression losses. We spoke about the binary loss functions, which is nothing but binary cross entropy. And then we have a different problem called that is used in multi-classification problems. Suppose if there's a big data set where the data set can be grouped into 10 groups, their binary classification will not work. The reason binary classification will not work is that because the outcomes are not 2. Here the outcomes are more than 2. Hence it is called multi-classification problem. So one of the classical examples we can talk is MNIST dataset. So it is an image classification problems which we can explore. You have an images, handwritten images of around many handwritten images, and all those handwritten images can be classified into 10 groups. If it is 1, it comes under the one bucket. If the number is 2, it comes under number 2. Here that problem is in multi-class problem. So when you are doing with multi-class classification problems, you will be using categorical cross entropy. You are using a loss function called categorical cross entropy loss function. So the cross entropy function, it consists of a softmax function as well as the log loss. So you all know that softmax function, it is a probability distribution. For example, if you have a problem where the output is the chances of that image being a line, the probability of that image being a line is 0.7, and the image that being a dog is 0.2, and that image being a cat is 0.1. So we all know that that image being a line is very high because it is point number 7. So when you have this type of cases, you calculate the cross entropy by taking the by taking the log of that number. You are taking the log of predicted value and you multiply it by the label value. So that's how you get it. You're taking the log. Here you can see you're taking the log of the softmax function and multiplying it by the softmax function. Am I clear? You're taking the log of the predicted value and you're multiplying it by the softmax function. This is how you are getting the and you are taking the sum and getting the average. This is nothing called categorical cross entropy. So I'm just summarizing the loss functions. There are 3 types of loss functions. One Are you able to see my screen, madam? Regression loss functions, binary cross entropy, and multi-classification problems. Okay. So these are the formulas that I have mentioned you. So this is the mean absolute error, mean square error, log. So nothing much we have already covered. Then the important thing that we have that we need to discuss is about the gradient descent. So what is the gradient descent? So gradient way is the way to adjust the weights and the bias. So the way by which the system can adjust the weights and bias is by using the gradient descent. So generally how the weights are adjusted is first when you do the first sample, what you do is you calculate the error, and the error you get by is by the difference between the actual value and the predicted value. And what you do to you is you take that value and go to the next sample and you find that error and you complete for all the records, and finally you compute the mean square error, and then you adjust the difference by using partial difference, and then you will get that is how you adjust the weights. The process of adjusting the weights is called gradient descent. So when you speak of gradient descent, there are three types of optimization that we can do. One is the batch gradient descent. So I think I will again pull up a spreadsheet which will help you to understand. Okay. So this is again a linear regression problem. So what I did was there are two sets. X is the independent variable and Y is the output variable. So my equation is this thing. Where is it? My equation is my slope or my x coefficient is 1.93 and the y and this bias is 4.27. So what I did was I predicted using my hypothesis. My hypothesis y is equal to 1.39x plus 4.27. So when I did it, I get a predicted value of 6.2. So what I did was I again calculated the difference between my actual value and the predicted value. I squared it. And when I squared it, what I did was I got a value of around 1.97. So this is my error. So what I did was the next step that I did was I want to calculate the slope. I know the slope is 1.93, but I want to understand how can we get 1.93. So I know if you plug in this value to any regression model, for example, when I plot these values and do the regression analysis, my system is telling me that the y coefficient is 1.9266 and my slope is bias is 4.272. So how does the computer calculate it? How does the system does it? So I just want to tell you how can we get this 1.93 by using gradient descent. Since I do not know the value of 1.93, that my m value is 1.93, what I do is I will take a random value, which in my case is 0.92, and I will take a random value, and once I do the random value, I plug those values into my equation, and I will try to compute the error. Once I compute the error, I will compute the square error, Once I compute the square error, what I'm taking you is I'm calculating the average of it. So here in this case, my average is around 6.47, right? You can see some 0.47. This my error is 647. I'm not taking the mean, but I'm taking the square error. So next iteration, what I do is I again change my value to some random number, which in this case is 1.03, and I again do it for all the samples and I will compute the value, the square error. Again, since I'm not sure, and I will again take a random value and again compute the square error, which in my case is 453. Again, I will do it for some other value. Some other value, you can see it, right? 1.43. My error is 244. 1.53. My error is 1.93. So 1.63. If you see, the error is reducing. 1.73. My error is 131. 1.83. My error is 114. 1.93. My error is 109. Again 2.03. My error is 114. You can see my error is increasing from here. 2.13. My error is 131. So 2.23. My error is 143. 2.33. My error is 195. 2.43. So you can see the error is increasing. So previously the error has decreased, and after some point my error has started to increase. That means my function has converged at some point, and after it has converged again, it is again diverging. So if you plot all these values in a two-dimensional graph, so when my m is 0.93, I got an error of 647. How you got? You can understand it. X, Y, my value is this thing. My predicted value is y equal to mx plus c. Y is nothing but predicted value. M is 0.92 into x1 plus 4.2. You are getting a value of 5. And the difference is between 5 and 7 is 1.8, because there is some rounding. So 1.8, and you're taking the square, it is getting 3, right? So that's how you got it. Same thing, you do the same for 1.03, you're getting an error of 545. Same thing you do for 1.13. Here is the 1.13 and you do it, you're getting 453. Likewise, I listed all this value that I got in this from this row n to r, and prepared a table where m is the slope or coefficient or the future, and then I took the square error of it. So I did for around 20 samples. So once I did it, what I did was I plotted them onto a graph where the x-axis is the slope and the y-axis is the square error. So once I draw a graph, I got a graph that has converged. I got a U-shaped graph. So you can, when I say the graph has converged, that means it has a minima. And here the minima in this case is close to 100, right? Close to 109. So here my data set has converged at a point, and the point is 109. So if you look into this, where does 1.93 come? So it is coming when the slope is 1.93. That means the coefficient of x, or the slope, should be taken as 1.93. You can see, if when you do, you take this data set and do an linear regression. Maybe if you want me to explain how you do it in Excel, I can teach you. But if you do the linear regression in an Excel or some other model, or R or Python, if any other case, you will get that this coefficient of this data set or the future say value of the coefficient x of that feature x is 1.93. How you got is just by trial and error method. So I am again repeating it. The way you do it is you start with some random value, then calculate the slope, again change that value by incrementing or decrementing to some value based upon your rationale, then calculate the square error, again do it, calculate the square error, then once you are calculating, then you plot all those numbers with the error on the y-axis and the slope on the x-axis, and you plot it. And if you are able to get a curve, U-shaped curve, when I say U-shaped, that means when you have an converged graph, that means that value, your model is good enough that it has predicted that the slope should be the value where it has got the minimum. So it is the minimum of around 1.93. We can do a projection and the projection says 1.93. So the entire process of doing it is called gradient descent. When I say gradient, the other word for gradient is a slope. And this the gradient means slope and descent means falling down. So once it is this is the point where the slope is minimum. Here the slope is high, falling, and it has reached a stage where the slope is 0. The slope for any horizontal line is 0. So if you take a point and draw a tangent, and if you calculate the slope of the tangent, then the tangent is an horizontal line and the slope is 0. So the point where it is intersecting the x-axis will become your coefficient of that future. Here in this case, our the coefficient of x is 1.93. So unfortunately, there is no need for us to do it. The logistic regression or the algorithms, they will compete for us automatically. But I want to give you an understanding how this gradient descent works. So as I told you, there are a few types of gradient descents. One is called this batch gradient descent. One is called the batch gradient descent. So here what batch gradient descent means is, so here in this case we are changing the slope, right? So we are adjusting the weights only after we have undergone for the entire records. Here in this case we have got around 11 records. So we have changed the weight m from 0.923 after we have iterated all the records. After you are done computing the square error for all the records, then you are computing the square error, then you are adjusting the weights. So this process is called batch gradient descent. The reason it is called batch gradient descent is that you are adjusting the weights after you have completed the entire batch, right? Here in this data set, for our example, our data size is 11. So what you did was you have updated the weights after you have finished iterating all the 11 records. For example, in a typical mission model case, the number of records that you will deal will be in millions, right? A typical modeling, the number of records that you have will be close to millions of records. So when you have millions of records, and assuming they are around 1,000 features, Imagine, so 1 million records and 1000 features. So likewise, you need to calculate the square error for all the million records. Once you are done with the millions of records, then you need to adjust the weights. So what happens if you have features like 100,000 features? Here in this case we are using one feature. If you have 1000 features, you need to do the same 1 million records for 1000 features. So it is getting computationally expensive, and it is not only computationally expensive, but also it is very time consuming. You do a simple math, 1 million records and 1000 features. So it will take a while, because for to change, to update the weights, you need to wait till all the 1 million records are completed. And once you change the next weight, again you need to wait till you complete the 1 million records. So it is very computationally expensive. At the same time, it is very time consuming. So in such a cases, when the data set is very big, you cannot use batch gradient descent, for which there is another model what we call as stochastic gradient descent, right? So what does stochastic gradient process do is, just a minute, I am opening my screen. Okay. Okay. So we have talked about this batch gradient descent. So all the records in the training sample are used, and then error is calculated, assuming 10 million records. The first adjustments of the weights is done only after processing all the 10 million records. Then it moves to the next iteration. So this batch gradient descent is only used for training small training sets. For example, 100 or 1000, maybe 10,000. If it is more, then batch gradient descent is not practically possible, because it gets computationally expensive. At the same time, it is very time consuming. So in order to encounter, or in order to negate the disadvantages by the batch gradient descent, there is another model called stochastic gradient descent. So in this stochastic gradient descent, what we do is, rather than waiting to process all the records in the data set, what we do is we select one record randomly out of the training sample. Let us assume you got 10 million records. When you have 10 million records, what you do in stochastic gradient descent is you will choose one record randomly. Once you choose one record randomly, you calculate the loss. The loss might be an absolute loss, or the mean absolute loss, or the root mean square error, or whatever it is. Then you calculate the loss. Once you get the loss, you have an understanding whether how big is the loss. If the loss is positive, then change the weights in one way, and if the loss is negative, change the weights in a different way, and then change the weight and again calculate the loss, then see the difference. If the loss is decreasing, you do it you again go with the next iteration. You change the weight to the next level. So you will do it till you get the optimum result. When I say optimum result, you will do this iteration till the loss you get is minimum. So you do this process for the end for just one record. So this stochastic gradient descent is used wherever the data set is big, is huge, and also it is used wherever you want to minimize the computation. For example, if you do not have access to a big high powered GPUs, and if you have a good system, if you have a good laptop or a good desktop, this stochastic process gradient can be used. So I'm again repeating, the stochastic gradient descent is, rather than iterating all the training samples of a data set, what you do is you randomly select one record. Once you select the record, what you do is you calculate the cost. You compute the loss. Based upon the loss, you modify the weights. Again, do the do the same for the updated weights. You continue this process till you get a loss which is minimum. So the difference between a batch gradient descent and a stochastic gradient descent is, this gradient descent, you will wait to update the weights only after you finish processing the entire data set. In other words, you will wait until you have transfers the entire data set. If it is 1000 records, you wait till the 1000 records are processed, and then you will compute the loss. If it is 1 million records, you will wait till you process the 1 million records. Then after you process, you calculate the loss. Based upon the loss, you update the weights. So batch gradient process can be used where it is good for training smaller data sets, and where you have good system resources, and stochastic gradient process is used where the data set is big and where you want to minimize the computation. And then we have the other type of optimization algorithm, which is called mini batch gradient. Mini batch gradient. Here what happens is it is similar to SGD. For information, SGD stands for stochastic gradient descent. So it is very similar to SGD, stochastic gradient descent, but only the change is that when you consider the batch in stochastic gradient descent, you are selecting one random sample. That means the data the data size is 1. This data size of that random sample is 1. But here in a mini batch gradient, the size of the sample is more than 1. Maybe if you have, let us assume you have around 1 lakh, 1 million records. You can select a batch size of 1000, and then you calculate the loss for the 1000 records. Then you compute the loss. Then what you do is, in the next set, you select another 1000 records and do the same. See the loss. If the loss is changing, if the loss is minimizing, keep on continuing till you get a loss which is the bare minimum. So comparatively, the mini batch gradient, you can the computation is drastically reduced, but it depends upon the case by case. There's no hard saying that you need to use the mini batch gradient, but in the real case scenario, you need to try with all these models and you can decide which model works good. So there are many gradient descent algorithms, but these are the few basic gradient descent algorithms. So these gradient descent algorithms, they are also called optimizers, right? So these are also called optimizers. So these optimizers, they are used to adjust the weights in a training process. So the types of optimizer that you frequently encounter are ADA-grad, ADA-delta, ADAM, momentum, Newton's model, RMS prop, and SGD. So these are the types of optimizers that are available. So you can use any of these optimizers. So there's no need for you to write the code. Everything is coded. You just need to specify what type of optimizer do you want to use in your machine learning model. So these are the things that I covered. We talk about the weights, we talk about the biasness, we talk about the loss functions, and also we spoke about the activation functions, and we also spoke about the gradient descents. So these are very important, and these are the very few basics that we need to use in order to perform any deep learning model. So then we can do an hands-on on and few problems. First, I will talk about a single layer perceptron. Single layer perceptron, I'm not going to dwell, but this is an very primitive thing. As I told you before, it consists of an activation function. So activation functions, if it reaches threshold, it will fire. If it does not fire, this thing. So I'm not going to dwell with it. So the problem with single layer network SLP is the disadvantage is it works for linearly separable data. And for example, this is a typical XOR case. If you predict if you plot the values of XOR operator, you will get like this. So the one in hollow circle, they belong to one circle, and these two belong to another group. So if you want to if you want to write a classifier which separates these two, it is tough. This SLP single layer perceptron cannot handle. So that's why it's saying that it works for linearly separable data. For example, the one in the middle between the blue and red dots, they are linearly separable data sets. So you can use single layer perceptron in order to draw a classifier. But if the data set is not linearly separable, for example, the one on the left, you see it is you cannot draw a straight line in order to separate it. For which you need an higher level polynomial in order to draw a classifier for non-linearly separable data. So SLP cannot be used for classification of data sets that are non-linearly separable. It works only for separable data, linearly separable data. So for which in order to solve the problems which are not solved by SLP, what we do is we use another model called multi-layer perceptron. So multi-layer perceptron is nothing but stacking single layer upon one and another. So single layer perceptron, multiple single layer perceptron stacked or kept on top of one another is called MLP. MLP stands for multi-layer perceptron. So multi-layer perceptron is used for handling data which are non-linearly separable data. So here in this single multi-layer perceptron, you will see there are a number of layers and each layer has a number of neurons. So multiple layer perceptron consists of multiple layers, more number of layers, and also in each layer it consists of a multiple number of neurons, and that it is called a multiple layer perceptron. So multiple layer perceptron can be used to solve this typical XOR problem. So we do not have time how to show it, but in case in the future if we have time, we can talk how we can use MLP in order to solve XOR problem. So then we will be using an MLP program in Python to recognize handwritten digits. So, as I again reiterating, the other word for deep learning, the other word for multi-layer perceptron is also called deep learning. The reason it is called deep learning is because when the number of layers in a multi-layer perceptron are high. For example, if you have a network which has around 1,000 layers, we call it as deep. The reason we call it as a deep because it has got more number of hidden layers. So for any model, there are three type of layers. One is the input layer where you get the inputs, and on the top, on the other side of that model, you have an output layer. So in between the input layer and the output layer, what we have a number of layers. So the number of layers in between the input layer and the output layer is called as a hidden layer. The reason why it is called a hidden layer is because they are virtually invisible to the end user. It is a kind of black box. You don't know what is happening inside the hidden layers. You know it's happening, but you cannot know. If you want to understand all the components, you cannot see it. So that is the reason why it is called deep learning. So in deep learning, you have a more number of hidden layers. In real world, you got more than one typical deep neural network. You have a minimum of 100 to more than 1,000 layers. It's called a deep layer network. Whereas a traditional neural network, it consists of 2 or 3 layers. So don't get confused when people say about deep learning. Deep learning is the same as a multi-layer perceptron, but you will have high number of layers and each layer will have multiple number of neurons. What it is called as a deep learning network. So this is a shallow network and this is a deep network. So there is a hidden layer and an output layer. In between you have one hidden layer. Whereas deep neural network, you have the same input layer and the same output layer, but in between you have layers that are hidden. So that is the reason it is called a deep learning network. So in order to learn what deep learning, how to work on deep learning, we got three, this how this works, which is an Keras is one of the framework by which we can implement deep learning. Keras, it supports these frameworks, TensorFlow, Theano, and CNTK. Either if you, Keras is just a framework which is built on these things. TensorFlow is a framework, Theano is a framework, and CNTK is another framework. And what Keras does it is a wrapper by which we can use TensorFlow using Keras. So it is easy to fasterly deploy. You can deploy within minutes. It supports all the major frameworks of deep learning. The major frameworks that most people use are TensorFlow, Theano, and CNTK. So even though the functionality of all these frameworks are the same, these things have been developed by different companies, and these are highly module and easy to get started. And you can it supports simple models to complex models, and there's a huge amount of documentation. So if you want to understand how this optimizers work, you can refer the documentation for your understandings. And the very good advantage, it runs cleanly. There's no problems when you're running with it. So a few things I would want to tell: what is TensorFlow, what is Theano, and then we can go. TensorFlow, it is a widely used, it is the most popular deep learning network. So the reason why TensorFlow is most popular is because it is an open source. For example, if you go 10 decades back, if you want to perform any deep learning network, it used to be so expensive that people used to purchase, and most individuals, since they don't want to purchase it, deep learning was kind of black box. Only big companies which have huge money on R&D were able to use machine learning uh, in the companies, because the access of getting deep learning framework was quite expensive if you go decades back. But now TensorFlow is getting more popular, and because it is an open source library, that means anyone with a good internet speed, they can use all the functionality that are available to suit their own needs. And another advantage of TensorFlow is it is built by Google. You know, Google is the #1 company, and all the big companies use TensorFlow, and all the popular applications, they use TensorFlow. Other deep learning framework is CNTK. It is developed by Microsoft. CNTK stands for Cognitive Toolkit. It is developed by Microsoft. The advantage of using CNTK is, for example, if your organization uses Microsoft products like MS Office, Azure, and all these things, then it suits their ecosystem. Microsoft ecosystems, like if you're using SQL Server database and using Azure, these things. So if you are already a Microsoft product, this using CNTK will be very, very good. And also Microsoft, it is also an open source framework. And the other model that we have is Theano. It is an it is built in Python, and it is purely a mathematical. The advantage of this Theano, it is it can evaluate mathematical operations more efficiently, and it is used for deep learning projects and works on it works it runs very fast on GPUs rather than on CPU. So these are the three fundamental frameworks which we should be aware. So I'm not going to cover, since we still have an half an hour. So I would like to run a small program where you can use an MLP in order to just a minute, in order to, let me start my Anaconda. Okay. Okay. I hope you are able to see my screen, right?
Yes, sir.
Are you able to see the black screen spider interface? Python 3.8, black screen. No?
No, sir.
Just a minute, I'm giving access for that. Now can you see it?
Yes, sir. Yes.
Okay. So this is a very, very simple program where I am using right, or you can say an artificial neural network to recognize handwritten digits. So that is outcome of this program. So it is in Python code, and are building an artificial neural network to recognize handwritten digits. So you can say that I'm using TensorFlow as my this thing, and the TensorFlow I'm importing it, and Matplotlib is a plotting library. NumPy is a numerical Python for doing mathematical, and the most important thing is you will find here I'm using a database called, where is it? Yeah, from keras.datasets import MNIST. So MNIST, it stands for Modified National Institute of Standards and Technology Database. So MNIST, they have an image, they have a data set of 60,000 images, and all those 60,000 images are handwritten digits. And for the 60 handwritten images, what we have is we have a corresponding label for each 60,000 images. So you can understand in this way. Imagine a table having two columns. The first column is the handwritten digit, and each handwritten digit has a label saying that if the number is X, it will show as if the number is 1, the label will be 1. If the label is 2, if the image is 2, it shows the label as 1. So that I'm importing the database from the Keras. It is importing from keras.dataset import MNIST. So what happens is once we run this command, so I think you are familiar with this, how to use this functionality. So when I run this thing, it has executed, and now my this MNIST data set is loaded into my system. So once I load into the system, so what I am doing is I am splitting my data into two groups: training and test. By using MNIST load set, I'm getting the data into xtrain and ytrain. So let us run this block. So it has loaded this data set into xtrain and ytrain, and you can see the image 17. It is showing as what? If you see the image, you know that is 7, right? That is 8. So the corresponding label of that number is 8. Okay. Um, so I'm displaying the image that has been generated. So once it is generated, what I'm doing is I am converting the image into a categorical data. So what I mean to say by categorical data is it is called as one hot encoding, one hot encoding. For example, deep learning involves working with matrix, right? For example, the number 8, what we do is we are converting the number 8 into a vector. For example, here we can see the number 17, right? Mm, So here 17, you have a number. You see, since we are using 10 digits, you will be getting a matrix where you have 0 to 9, where you have a numbers from 0 to 9. And if the number is 1, what happens was, instead of where you have 0, it will showing as 1. So that's what encoding means. So what I did was, I have encoded the labels into one hot encoding. So when you what it does when you're doing hot encoding is, it changes the label into a vector. So this is very useful when you're doing machine learning operations. So if you do not convert into a vector, your program will not run. So here what it does is, my image has been converted into a two categorical data. In other words, you are converting the labels into vector format. You are converting the number into a vector format. So once you are done with it, so this is this I think MNIST, right? Okay, sorry about that. Yeah. I'm talking about CNN. Okay. So I think everything is the same here. So what I did was, it is just an simple artificial neural network. So what I did was, since I told you multi-layer perceptron, it involves stacking multiple layers one upon another. So what I did was, I am taking the input from my input image, then flattening it out. The reason why I need to flatten it out, the problem with artificial neural network is, the image is in 2 by 2 format. For example, I will show you one thing. Okay. So this is the image. It looks like a number 2 or number 5, whatever it is, image, right? So when the system is reading an image, you can see it consists of numbers here. See, there's the numbers, right? So you and I see an image, but how the computer sees an image, it doesn't see images, but what it sees an set of numbers in a two-dimensional format. So it is a 28 by 28 box. It is a grid of 28 by 28. In other words, it is a two-dimensional vector, right? So for an artificial neural network, what we need to do is, we cannot use a two-dimensional as an input. What we need to do is, we need to convert the two-dimensional input into a single column vector. In other words, we need to convert this image 28 by 28 image into a single row vector. So in order to do that, what we do is, we just convert into a 28 by 28, it is 784 vector, 784 sized vector. So what we do is, we copy this and paste it so that you have a single column vector. So here you can see, what I did was, I took it, I have flattened it. Like for example, I took this thing, I use the transpose. Again, I did it, copy it. Like I did for all the 28 rows. So what you get when you are doing it is you are getting a single row vector, right? That is what I call it as flattening. Am I clear? It is called flattening. So once you flattening it, you are going to get a matrix of this size. What is the size? 784. How you got 784 is the sample images in the MNIST dataset is 28 by 28. So 28 into 28 gives 784. So what I did was I converted my two-dimensional image into a single column matrix, and then I'm going to feed this as an input to my neural net. So once I do it, what happens is, oops, okay. So what model.add flattening, what it does is it takes the input, which is 28 by 28 shape, and then converts into a single column vector of size 2784. In other words, 28 into 28 two-dimensional image is converted into a single column matrix of size 784. So then what I did was I added another layer called dense layer, and it has an input of, it has a got of 10 neurons. The reason I took 10 neurons is because this is going to be the final layer, and we know that in this MNIST dataset, it has got 10 unique labels: 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 9, 10 unique labels. So that's the reason I took the final output layer as 10. And then I took an activation function of sigmoid, and then I ran it. So once I run it, what it says that it is throwing some error. Let me run it again. Okay. So it has created me a model saying that a model of sequential one has been created, and the first layer is the input layer, and the second layer is the flattening model. So you can see the name of the layer is flatten, and the shape is 784. How you got 784 is because we are converting a 28 by 28 image into a flat into a matrix. That's the reason why you got 784. And the next layer is a dense layer. What is dense layer? You got 10 inputs and the activation is sigmoid. So as a result, you got another 10 more. You got the shape of that input layer of that dense layer is 10. And you got total number of parameters are 7850. How you got 7850 is 784 times 10 plus 10 neurons have biases plus 10, you are getting 7850. And once you run this model, and model is a model dot, I'm using the categorical cross entropy, which we told you earlier, and optimizer is Adam, and the matrix is, when the matrix is accuracy. And once you run the model, my batch size is 32, epochs is 30, I think 30 will be too, let us take 3, verbose is 1, and validation bit of 20. So one I ran it. So what I get is once the model is run, so with 2 layers network, my accuracy was around, you can see 92.84. So that means this model is performing much efficiently. So this is what it is, a single, it is a simple multi-layer perceptron having only 3 layers. One is having only total of 3 layers. One is the input layer, other is the flattened layer, which is also called the hidden layer, and on top of it there's another layer called a final layer called dense layer. So this is how you get it. So if you want to see the plot, you can see the accurate the one in the bottom is the efficiency is the loss, and the above is the efficiency, right? You can see the two graphs. So the one is the validation, another is the test data set. So that is what we call a simple artificial neural network that is used for classification of these things. So before the next thing is, let us also talk about this CNN, CNN, which I can tell you, and then we can wrap up. We do not have time to go into the code, but at least I can tell you a few things. Okay. So the CNN, it is an extension of this artificial neural network, and the main difference between CNN and artificial neural network is so that the CNN consists of one input layer, but it consists of more or one or more convolutional max pooling layers. While as in multi-layer perceptron, you don't have this convolutional layer or max pooling layer. You have one input layer, output layer, in between they are hidden layers. But in CNN, you got few layers which are called convolution layers and max and pooling layers. And then you have this fully connected layer and output layer. So the problem with multi-layer perceptron is, if you have an image that is around, let's say assuming 1000 into 1000 size image, then when you're flattening it up, you are creating a very computationally big matrix. So it is very computational expensive. For example, 28 by 28 is small, but if you have a same image of 1000 by 1000, then you are having a 1000 into 1000, that is around 10 million, 1 million records. And then you are doing a fully computed this thing. As a result, it will be getting more and more expensive. So in order to mitigate the disadvantages of multi-layer perceptron, CNN is used. The CNN basically consists of the convolutional layer, stride, padding, pooling, fully connected layers, and dropout and softmax. So let us talk about this. What does convolutional layer means? So convolutional layer, it is nothing but this is an, let us assume it is an input image. In the MLP that we have taken a 28 by 28 image. But here in this case, for this example, let us take an image. Let us assume that the size of the image is 5 by 5. And what you do is you are going to take a filter or a 3 by 3 matrix. This is 3 by 3 matrix is also called as a filter, also called as kernel. So what you do is you will overlap this 3 by 3 matrix onto the input image. And then once you overlap it, you will do the dot matrix, dot multiplication. When you say dot multiplication, so 1 multiplied by 1 plus 1 multiplied by 0 and 1 multiplied by this thing, and you sum up it all. Then when you sum it, you are going to get this the number 3. Then once you do it, you are going to move the filter to the next level. So when you're moving to the next level, what happens is when you move to the next level is and do the same operations is, so it will move one step to the right. So it won't be here. It will from 2 3 4 2 3 4, and again you are going to overlap the same thing, and you are going to do the same thing. As a result, you will be getting the number 3. Likewise, you are going to do for the entire image, enter 5 by 5 image, and then you are going to get this number. So you are what you did in convolution is you are taking a filter and you are overlapping onto the on the input image and sliding to the right. Once you reach the right hand, you are going to move the layer down and again go to the right. Likewise, you are going to finish for the entire image. And then as a result, what you are going to do is you are getting an image, 2x2 image. You are getting an two-dimensional image which has reduced size. Here in this case 5 by 5, but when you are using this convolution, what happens was you have reduced the size of the image. Your 5 by 5 image, you have reduced the image to 2 by 2 image. Likewise, if you take a bigger image and you are going to do a convolution with the 3 by 3 filter, what you're going to do, what you're going to get is you are going to get a matrix of 4 by 4. So what happens is you are reducing, you are in other words you are doing the dimensional reduction. In 5 by 5 image has been reduced to 3 by 3. Likewise, by changing the stride or by changing the size of the filter, you can reduce as per your needs. The next thing is the stride. So here in this case, we are moving the filter. We are moving the filter one by one. So after you do it, the filter will be moving to the second position. Then you do the sum, and once you calculate the sum, you are going to move into the third row. Likewise, the stride is 1. So there is a possibility by which you can move the slide by factor of 2. That means the stride here is 2. So that means after performing the convolution on the particular thing, the filter will move by 2 steps. These are all the hyperparameters by which you can choose at the time of coding. So once you do it, then we have a called what is called as pooling layer. So pooling layer is nothing but here let us assume it's a 9 by 9 image. What it does, I'm taking a 3 by 3 matrix here, 1, 22, 78, 86, 1, 32, 54, and then you are doing the sum and adding it up and keeping in this layer. As a result, what is happening is your image, which is of original size of 9 by 9 image, has been reduced to 3 by 3 sized image. So this is what it is called. There are many types of pooling. What we have used here in this case is the max pooling. So after this number 22, 78, 86, 1, 32, 54, 82, 29, 64, after these 9 numbers, we take only the number which is the highest. As a result, the highest number is 86. Then go to the next thing. Here from 4, 6, 21, I think the highest number is 66. So this is what it is called as max pooling. There's another called as average pooling. Average pooling is nothing but instead of taking the max, you are taking the average. And also there is called another thing called as sum pooling. Sum pooling, rather than taking it, you are taking the sum of the entire 9 numbers and having it. So I will show you and demo how a CNN works, and then we can wrap up with this session. So this same what I did was I just written a small code which will do the same, recognize a handwritten digit using CNN. So only difference here you will find here, you will see that we are using convolution and layers called pooling layers. So here the model is sequential because we are stacking one layer upon another layer. Here the first layer is the convolutional two-dimensional, by which the first number states the number of filters that you want to use. Here I used 3 filters. Then I used a kernel size of 5 by 5. Kernel size is nothing but the filter. The filter is 5 by 5, and then I am planning to take a stride of 1 in the row direction and 1 in the column direction. That means 1 by 1 row column direction, one step row wise and one step column wise. and then I'm using an activation function, and I'm giving the input shape of 28 by 28 by 1. 28 by 28 by 1 is nothing but the original shape of the input image. So once it is done, I am converting this max pooling. So my max pooling is 2 by 2 matrix, again straight of 2 by 2, and I name the pooling as this thing. And again I added another convolutional layer of size 2, and I did it. After I am done with it, what I did was I used an flattened, which will convert a two-dimensional image into an one-dimensional vector. Once I am done, I am doing flattening, and let us doing this thing dense layer, then let us done it how it works. So I'm covering at a very high level because we are running out of time. So this thing, yeah, this is the main network. So you can see the image is 28 by 28. It has been converted, it has been downsized to 24 by 24 times 3 filters. Here 3 means number of filters. I have specified that the number of filters that I want to have is 3. So what I did was, what the output that has given me is, it has given me 3 feature maps of each size being 24 by 24. And then what I did was I did the max pooling. So max pooling, what it does is, my pooling size is 2 by 2. So what it does by it takes the 2 by 2 and it will downgrade. So my size has been reduced to, from 24 it has become 12. So then I'm again doing a convolutional layer of two filters of having size 3 by 3, activation of 1, same thing. And again after it's done, I am again doing it in max pooling. So max pooling 10 by 10, due to max pooling the size of my image will be reduced by 2, by half. As a result you are getting, so I'm flattening. What I got was, I got a flattened image of 50. So you can notice the difference between CNN and this thing in CNN and ANN, artificial neural network. And in the artificial neural network, the flattened layer is 784. But here, by using a mix of convolution and max pooling, what I got was, I got an simple single layer matrix of around 50. So I got a reduction from 784 to 50, around 10 times reduction I got it. But this I got it without losing any information. So what I did was, again I connected to this from here. It is nothing but the simple multi-layer perceptron, and then let us run this model, how it goes. So the running model is done. So you're getting a model of this thing. So let me fit this model. Since we are running out of time, I'm just keeping 2 epochs. I don't know, something went wrong. Okay, so once you run away with this, I think the main important thing that you need to understand is, you have by using CNN, what you have done is, you have reduced by using a combination of convolution layers as well as a combination of pooling layers, you have reduced a size of 784 image to an 50 image, 784 single matrix image to 50 flat image. As a result, without losing any information, without losing the spatiality, or without losing this location specific data, you are able to maintain the spatiality of that image. Thereby, you are increasing the efficiency of that algorithm. So that's it on CNN. If you have any questions, let us take up, because since we are running out of time. So any questions on CNN?
Dear participants, you can ask the questions. And thank you very much, sir. It's such a very nice session, sir.
Yeah, thank you very much. I wish I could another 10-15 minutes I can continue, but we are running
Yes,
out of time.
yes, sir. Again, we have to start session 3, sir.
I know. I know.
Yes, sir.
Yeah, thank you very much. Thank you for giving me this opportunity, and I wish I will meet you again face to face in
Thank you,
future.
sir.
Thank you very much. Bye bye.
Yes. Dear participants, please have a break from 1 o'clock to 2 o'clock and again join the session 3 by 2 p.m. Thank you, sir. Thank you, one and all.
Madam, LLP madam. Hello, madam. Pranita
Sir,
madam. The session 3 was
sir,
postponed,
Chapin, sir.
madam, due to some administrative problems. The session 3 will start at 4:30, madam, today, 4:30 to 5:30. Please
Okay,
announce
sir.
that thing, ma'am.
Dear participants, session 3 will start from 4:30 to 5:30. Due to some technical problems, it was postponed. Thank you.
So everybody should connect
Please
it.
join by 4:30.
Yes, ma'am. The same thing will be intimated in WhatsApp group also. Please make a note of that.